cosmic storm. Floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light. Riding the waves that are just out of sight.
It's that time again. It's time for Whimsical Wavelengths, where we uncover the best scientific pickup lines like this one for all those geophysicists out there. You must be a gravity anomaly because you're attracting all my attention. This time on Whimsical Wavelengths, we're going to explore machine learning and artificial intelligence applied to geophysics. Computer overlords rejoice. No, really, though. Artificial intelligence and machine learning are extremely useful in scientific applications. No copyright issues here. I think actually this is going to be the first time we've really applied or really using artificial intelligence or machine learning as part of the underlying science. Yes, here in Whimsical Wavelengths, it's come up a few times when talking about certain topics on different aspects of science, but usually really kind of near the end of an episode where you're like, where is this going for the future? So where to start for today? I guess what is geophysics and inversions seems like a good place. Geophysics is basically combining my two favorite subjects, geology and physics, together, using physics to study the Earth, its structure, and its processes. And geophysical inversions, that one ends up being a little bit harder to define without using a bunch of jargon. Here is going to be our starting point. It's going to get a lot more technical, especially once our guest joins us. A geophysical inversion is a mathematical process of estimating the distribution of physical properties like conductivity, density, or perhaps even velocity, wave speed velocity, if we're talking about seismic data. We're looking at these properties beneath the Earth's surface from measurements collected usually on or above the Earth's surface. So obviously when it comes to the Earth, we're not able to tunnel really easily. So when we try to measure something, we're measuring it at the Earth's surface. We can't measure these properties directly in situ. I'm not going to be there at a kilometer beneath the Earth's surface with a ohm meter measuring the resistance of all these rocks everywhere underneath the Earth. It's just not feasible or possible. So inversions are special because they use the physical properties or the physical measurements that we take on the surface and then work backwards to infer what the Earth must be like to produce those observations through solving the physics through mathematics. The data itself, though, I've spent years of my life doing this and collecting it across the most remote places in North America. The data is typically collected via helicopter walking across the terrain. Me, I was doing this on the ground, meaning I was walking many kilometers or miles, carrying wire and instruments across hills, swamps, and mountains, and everything else in between, pushing buttons and problem solving. And problem solving is a really big thing when you're hundreds of kilometers from the nearest road or town of anything, meaning if something breaks, you have to kind of cobble it back together to continue to collect data, or handling crew dynamics when somebody wants to quit or doesn't like somebody else. My point here is that the data it can be really hard to collect. Some examples of data that you can collect are measuring changes to the Earth's gravitational or magnetic field over space. So walking across the Earth's terrain, pressing buttons, collecting how that field changes spatially. Or looking at how magnetic fields or electric fields travel through the Earth. So once we have the measurements, the inversion, like I've already alluded to, is a mathematical way of taking those measurements and trying to get something, or looking at how different physical properties change beneath the Earth's surface. To get a model, particularly a 3D model of the Earth, requires a lot of assumptions and simplifications because there are way more unknowns than knowns. We're collecting data at the Earth's surface and trying to infer what's going on deep beneath the surface. Broadly speaking, that means we have an infinite number of solutions or models that can reproduce the data we've collected at the surface. Today, we're going to explore tools that we can use to limit that number or infinite number and illuminate what we cannot directly observe. We're going to illuminate the void of nothingness. You know, some people fear the void or the unknown, but geophysicists just call it a zone of low sensitivity. Time to dive in and bring in today's guest. Like myself, he spent time in rural areas of the world pushing buttons and pulling wire across the landscape. Differently, though, he's much more mathematically inclined to build the tools I'm privileged to leverage to probe the Earth. So, today, please welcome my coworker, PhD candidate at University of British Columbia, and geophysical guru, Jonathan Kataj.
Oh, thanks. Thanks for having me on the show, and such a great introduction. That's great.
Short and sweet, but we'll get into all of your backstory in just a second. First, PhD land, at least that's how I called it when I was there, using as little jargon as you can, which is always tough. Describe what you expect your thesis will aim to answer or investigate.
Yeah. Well, I guess as simple as I can. So I'm using like image segmentation methods, which are usually not typically used in geophysics. And I'm trying to use them to answer the questions of how we can resolve our subsurface images better, given our data. We tend to use really kind of just regularizers, and they're pretty general. We're just looking for smooth models, and the images they're not so much blurry. They're a whole bunch of stuff. They're a whole lot of everything. Well, but what I'm trying to do is use segmentation methods to help resolve that.
Okay. Image segmentation methods. What are those? I mean, I'm playing coy because I know more than your average person, but I don't feel like the full explanation. Like, what is? Everyone knows what an image is. So, what is image segmentation methods? Like, give an example from, I don't know, using some AI thing like recognizing streets or something.
Yeah, well, we could even relate it to, self-driving cars. They've got to take their images or take in images and be able to isolate structures. So it's, I guess, if you want to put it down to it, image segmentation is just trying to identify areas of commonality, and it kind of gives boundaries to objects and structures that you are able to then interpret.
Okay, and then you're using this to look inside the Earth, I guess. You're trying to use images of the 3D models that you can build from doing things like geophysics that we infer that they're fuzzy, and then you're adding this process to try to infer structure and boundaries instead of something fuzzy.
Yeah, exactly. We're just trying to find these edges, or just highly define these structures in the subsurface. And by using these image segmentation, we can kind of refine and improve our regularization to be able to pull out more like geologically real models.
All right, another deviation. Regularization. What is it?
Yeah, it's pretty much the term in, I'm going to probably use some more jargon here, in the objective function. So some kind of function that we want to minimize. But yeah, to make it easier, is the regularization holds all our prior assumptions, all the knowledge that we know or what we expect for an outcome of the model that we try to create.
So you can use this word regularization on any problem that you're adding prior information on, whether it's topography or anything that you're trying to I keep wanting to use the word invert, but I'm also trying not to use jargon. So
Yeah.
Any problem you're trying to solve through mathematics, the regularization is providing some kind of structure to the solving of that problem. Is that fair to say?
Exactly. We're just trying to give it as much information as we can on what we want to expect out of the model.
Awesome. So now we're going to back up before we go forward, because to get to PhD land, your journey wasn't exactly a straight line. So what was the winding path that brought you to this point of the world?
Oof, that's a long story. But well, first, kind of similar. I really liked dinosaurs. I really liked volcanoes back when I was really young. But then I kind of just wandered into math and science land and thought I would become an engineer first. So I tried that, and then then I found a geophysics class, and it really hooked me. So I decided, well, I'm going to go and do my bachelor's in geophysics. So I went and did that, and after 4 years of first doing engineering and then into geophysics, I really wanted to get into industry. So then industry, I joined an data acquisition group, and just toured the world, collecting data all over the place, all sorts of data, mostly what we call direct current resistivity and induced polarization, where we're just injecting lots of current in the ground and mapping electric fields. And then from there, I don't know, I guess I got a little bored. So then I got into programming, and then I started writing software to do signal processing. And then I joined another group that had a lot of data. So at the time, the stuff that we used, like the software that we used to interpret that data, was insufficient. So that made me get into inversion, which I joined a group called SimPeg. It's an open source group out of the University of British Columbia. And I played around with them for a while, which then, they kind of grew on me. And they're like, well, John, why don't you do a PhD? So here I am.
Yeah, I guess that's one thing we definitely share in common. Although, I gotta say, I was only really within Canada when I was traveling about pushing buttons. You really got to go the whole world. So at some point, I will circle back near the end, and you're gonna have to give us a story of the craziest place you've ever gone or the craziest event, without giving too much away, so you don't get in trouble. So there's
fair.
always, as we've been kind of alluding, like you went and collected the data, then you got into inversions. So there's always two sides to this, two parts, which might be a whole side discussion: the data and what happens afterwards, or in our case, for our day jobs, the inversion. So let's dwell on the data just for a moment before we get into the more technical stuff. Like, how is the data collected generally? Like, what's involved?
Well, it all depends on the survey itself, but the common, like the ones that I've been into, electromagnetic surveys. Oh man, yes, it's a very impressive, the logistics that you have to do to carry out one of these surveys, bringing in kilometers and kilometers of wire, dragging that through bush. There's not always a path, so you're gonna be on snow. You're in snowshoes, climbing hills, swinging from vines, all
Well, maybe
over the
not
world.
swinging from vines.
Well, actually, there was a time in Mexico. We were in a pretty steep topography, and the vines were helping me climb those mountains. So maybe I wasn't swinging from them, but I was holding on for dear life.
Okay, so it's a lot of hard work is really what it comes down to in some really remote and special places sometimes.
Yeah.
So inversions, building off what you've already read in the intro, I set a basis for what geophysics is and what an inversion is. One term that I danced around on purpose was the term ill-posed problem. So in our context in geophysics, what does that mean?
Oh boy. Well, the technical term would be it's the null space, the space of infinite kind of models that we can actually fit our data. Simply what I could put it as.
Sure, but I don't think anybody outside of taking university math has ever heard of a null space. So, I would it be fair to pose it as if there's more unknowns than knowns? You have less real world data and more things you're trying to solve out of an equation. So there's too many possible solutions to solve that set of equations.
Exactly. It's just an underdetermined problem, usually is what's the case where, yeah, again, you're solving for this model that's discretized up the subsurface, and it's usually millions of parameters, and you might only have, dozens of data. So that is exactly what it is. It's just very underdetermined. You're trying to solve something with less knowledge than what parameters you're trying to solve for.
Right. Well, you've also just recently got your first paper published. It is published now, is it not?
It's on its way.
It's on its way, but it's been accepted. Is that where it's at?
Yeah, it's just that long story short, they're changing the system. I have to submit to the new system, and then it goes through.
Okay, so it's accepted, but has more bureaucratic hoops to go through.
Oh, you bet.
Okay, so that paper, which is the first of your PhD, so congratulations on getting that through the system, because that's always a pain in the butt, is learning structural information through inversion using image segmentation methods. So first, where did you submit it, which is a bit more of a question of the sausage of science, and why specifically there?
Yeah, so I submitted to the Geophysics Journal, so that's kind of run out of the SEG in the, well, I guess it's very international, but it's the Society of Exploration Geophysicists. And yeah, I submitted to that one primarily because a lot of the work is based off of papers that were published in that journal. Um, the original one was by Doug Oldenburg and Yagwo Lee, and they were looking at how you can just how do we form these regularizers to contain more of our information, our prior knowledge, and they found a way to be able to take its principal axes. And when I say principal axes, it's kind of like your model space. So, and we live in a 3D space, so we're going to have our x, y, and z axes. But in mathematics, we can change that. We can rotate that coordinate axes so that it's kind of pointing a little bit down, a little bit up. And that's essentially the work I built on is upon theirs, because now I have a way to be able to take spatial information and prior knowledge of dipping directions or like straight layered stratigraphy, and I can program that into every cell in the model so that I can tell the regularization exactly what, like, I need to be able to, I want structures in this direction. And that's also another common, or not, maybe not a common theme in geophysics, but a lot of the geophysics papers are kind of the application style. It's not so much the theoretical, but how we can take that theoretical and then add it to our toolbox.
Okay, so I guess that answers the question of why you put it in geophysics, because the people that, or that journal really specializes in these sorts of methods-based papers.
Yeah, it's an application of most of them. There, like, it does do theoretical, but a lot of that's like the papers that I followed up on all structurally built, all the structure that I built from is from this geophysics journal because it's an applied journal, and that's what I'm doing is I was trying to find a way to apply some of this a priori knowledge to an application.
Okay, so we're going to do one of my favorite things to do as part of the show and take something I had no idea what it was when I first read it, spent a lot of time trying to figure out what it actually meant, and then still not sure. But better off than when I started, to be fair. So we're going to do some fun sounding jargon. Applying a Gaussian mixture Markov random field. I bet most people here have at least, or listening, have heard of a Gaussian distribution or normal distribution. It's probably the distribution characterized by, it's the symmetrical bell-shaped curve. Fun fact, this is how some professors curve grades. You can totally dump on Gaussian there. Grades too terrible? Yeah, just adjust it so it fits the Gaussian distribution. In my own experience, and in actual fact, it's rarely done. I think I've only had it done 3 times out of every single course and test that I ever took. But aside over, what is this thing? A Gaussian mixture Markov random field.
Yeah, I really just go with the GMMRF. It's even that one's hard to say. It's just yeah, it's a mouthful.
Jimmerif.
Yeah.
Jimmerif.
But yeah, essentially it is yeah, it's a special kind of Gaussian I guess Gaussian distribution. It contains multiple, so you're going to have many means within this Gaussian mixture model. So it's pretty much what the name says. It's a mixture of individual Gaussians. However, what makes it a Markov random field is that you can encode spatial information into it. So those Gaussians know how to talk to each other in space.
So you have a bunch of bell curves that are distributed in space that can modify each other.
Yeah, depending on how close they are spatially, not just necessarily how close their means are. They could have close means, but they could be very far apart. And these Markov random fields help us be able to encode that into our Gaussian mixture model.
Okay, so the idea is that your mathematical algorithms or formulas or equations, the inversion, in other words, has a series of these Gaussian distributions within it due to structure or a priori information.
Yeah, typically it'll be like a physical property. We'll have an idea of how many kind of rock units that we're going to expect, and those will be assigned a physical property value, which stands for a mean in our Gaussian mixture model.
Okay. So you can imagine, audience, and correct me if I'm wrong, if I overstep my skis here. Um, I've been known to do that. But you can imagine if we just take a layered Earth, which is rarely the case, but if each individual layer had a different mean, each one of those represent a different Gaussian, and each one of those is also representing a structure. And so you have these individual Gaussians or layers that can affect one another within the inversion or the ill-posed problem we're starting with. Is that kind of right?
That's pretty bang on, yeah.
Perfect. Okay, so when we start talking about structural information, which is almost a jargon term in itself, because to those that are just jumping in somehow into the halfway through the podcast, you might be thinking like we're building something. Is it? It's definitely not like creating a city under the ground, though, is it?
No, it's I wouldn't say creating anything underground. It's just trying to interpret from the data what this subsurface image would be.
Okay. Maybe to bring this together and make it make sense of why this is kind of a big thing, like it is actually a huge step forward for people in our sphere for inversions, is let's go back to what a classical geophysical inversion is, also known as the unconstrained inversion. When it comes to imaging geology, I know we can image or illuminate it really well, but generally, where do they fail?
Well, they fail a lot, mostly because of their sensitivity, depending on the data set that you're using and what you're trying to detect. So we're going to have lots, like, again, this comes into that ill-posed and this null space. There's so many models. So we've got models that can have very thick, say, conductive, so meaning, currents travel really easy in these layers. And if that's over top of anything that we're actually trying to target, we're not going to be able to see it. It's going to suck up all that kind of imaging power, all that current, and we're only going to see some kind of conductive layer. So these really break down because in a standard L2, you've got no other way. You're just like, I want a smooth model. So you're just going to get this smooth conductor on top. Whereas when we can start modifying that L2 and putting some more information into that regularization, we can start trying to see like, okay, we expect something to be shallower, but we want stuff to grow at depth. That's where we're going to get our advantage over our standard L2, as I call it, or the unconstrained inversion.
Yeah, maybe this is like, again, I'm very much a user audience when it comes to inversions. I'm much more of a closer to the geology side of geophysics than John is very much within the mathematics and able to program some of this. So I'm going to take a stab at this a little bit to illuminate the fact that we've used the term L2. And that's just, if my understanding is correct, and hopefully it is, it's just another way of putting in our prior information. We're making an assumption to be able to solve the ill-posed problem, and L2 is a way of bringing in that assumption, which assumes kind of a continuous, smooth property distribution. So it's going to try to smooth it out a little bit. It's not going to give you true layers. It's not going to give you hard boundaries until you do something to it, in which case it's no longer constrained. Is that about right? More or less?
That's completely correct. Because as soon as you start wanting more out of the inversion for details and boundaries, you're starting to you want to put weights or hard constraints at certain places and certain spatial areas in the model.
So in other words, the L2 it is fantastic when we have no other information. It provides us something that can track geology fairly well, but it's always a really kind of fuzzy image of what the real thing is. It's like, for lack of a better way of saying it, it's like looking through a number of different glasses, and each one is distorting the image a little bit more and a little bit more. So it kind of blurs it out. But in geology, it's often quite a stark contrast. When you hit a lithology boundary, you're really going from one property to the other. So this smoothness doesn't really break down. So perhaps it would be useful to state why we don't typically force that onto your standard unconstrained inversion.
Yeah. Well, the way to explain it mathematically is that the L2 is just a beautiful function. It's differentiable everywhere. It's smooth. It just works mathematically nice. When we want to start imposing in some of these a prior information, or say we want to use norms that aren't smooth, that gets mathematically hard, and it's not doesn't always want to converge. You don't always get to an actual model that satisfies the data.
Well, let's take a tact back towards your paper. There's lots more we can get into, but I think for understanding the paper, we need one more component before trying the results. Neural networks, the AI or machine learning component of the paper, which, if you're going down that road, I really hope you're not working at replacing me.
No, definitely not. Most of the work that I do is it's using we're employing it to be a tool of ours. So like that's the thing. The what my paper was built off of is rotating that regularization, being able to encode the information into it. So technically, you don't need the segmentation or the AI. If you have an idea, you can put it in yourself. But what I'm working at here is being able to, let's make the computer do the work for us. Why do we want to go out and measure dips and look at orientations and spend the time assigning these ourselves when we could actually have just a model that can, you know, take that information or take in the information that we have or the images that we have, geology, and then it can spit out information about the orientations and the structure directions.
Okay, so I guess there's two questions overlapping here. First, so you're getting the AI or machine learning to pick out an appropriate structure to try to seed or use as prior information to the inversion. But like any machine learning or AI, you've had to train it on something, and I assume you haven't stolen a bunch of inversion models from across the internet and trained it on it. So um, maybe just explain that part a little bit for the audience.
Yeah, well, at first, that's the avenue I started to look at is, well, you got these models, you have to train it on something that you're looking at. It's not very generalizable when I first started. But then trying to make examples, it takes a long time to run inversions. So getting a huge sample base was not really a thing. It was just not tractable. So though I didn't steal anything, but what I did was is I've that the actually it was the spring right before I started getting into this, the SAM model, segment anything model from Google or from Meta was released, and it looked really great. They were trying it on all sorts of images, all different sorts of things. So I'm like, well, let's take a crack at geology. Let's see if it can look at a geophysical inversion and segment out objects. And lo and behold, it actually worked really well right out of the box. And with these models now, they train them on the whole internet or what have you. And yeah, they put these models, these checkpoints up, and you can download them and you can start from there. So even if I wanted to, or I could, if I wanted to, is then use some of the geophysical inversion kind of examples that I had before, and I can fine tune it. But I found that I actually don't have to. The SAM model is quite great, and it's a great segmentation tool.
Whoa, wait a minute. So you just took something that is trained for something else, completely I mean, it's similar. You're finding structure and identity and shapes and things,
Yeah.
but you could just take that and apply it directly into this branch of science, and you didn't really need to tinker with it?
Yeah. So they call it foundational models. So I've found a foundational model that's applicable to the geophysical inversion and tried it out, and it works. You could something that was trained on ice cream trucks can actually also find segmentation in geophysical models.
Wow, that's awesome. Okay, so now the results, because we've got the ill-posed problem, how we're going to add information to that ill-posed problem through image segmentation, so identifying things that are created in the model by solving that ill-posed problem, things that have structure, and applying that structure and essentially rerunning the inversion, I guess.
Yeah.
Yeah, okay, I saw the head nod. So you're going to go through that process. So what is the case study or proof of concept for this? Set the scene for us. Where was the data collected?
So the data is collected in the wonderful Athabasca Basin. Well,
Oh,
this
I
is where
know it
my
well.
oh
We
yes,
both do.
nice cold winters and lots of skidooing and fun.
And a lot of bugs in the summer.
Oof,
Holy smokes.
too many
For
bugs.
those listening that don't know where we're talking about, the Athabasca Basin sits in northern Alberta, and it's actually mostly in Saskatchewan, but it straddles the border there. It's got a big lake, it's a sedimentary basin, thick sandstone layer above it. Sandstone high in quartz. Quartz is a resistor. And then beneath it is the old rocks of the craton. So the oldest rocks of the world actually sit in the North American craton. I don't know about the area of craton here, but it's certainly more than 2 billion years old. I just can't remember how old the craton is beneath the Athabasca Basin. But back to setting the scene.
So in this setting, we're gonna have lots of structural faulting happening across that interface between the sandstone and the basement, and this allows hydrothermal fluids to drain upwards, and they carry a lot of mineralization or fluids, hydrothermal fluids that are going to mineralize and deposit uranium at these boundaries or near this unconformity. And these faults are really huge, so they form these long dipping conductors, or yeah, they form along the faults. So they're not quite sheet like, but they're very dipping like objects, and that is essentially what a great kind of object for image segmentation. And the idea is we want to be able to tell where these conductors are faulting to, or where they're dipping to, so that we can plan the drill holes accordingly. We kind of know which direction to step out as we kind of probe these conductors. And then we also have these horizontal kind of unconformity over top of them. So if we can start looking at, we can start segmenting structures that are not flat lying. We can get kind of a dip approximation out of those, and then we can also get kind of the thickness of that resistor on top as kind of a segment outing, like flat layered blocks.
All right, before I try to summarize the whole picture here, because I think you've done a good job for me. How thick is the overburden here?
Varies a lot, but
Just give me a...
generally about 500 meters in the areas that I'm looking for.
So yeah,
But
it's
it could
quite
be
deep.
250. Yeah.
So for all the listeners, you can imagine you have, because it's Saskatchewan, it's pretty flat. So you have flat plains, lots of lakes and trees and swamps, and then 500 meters. The top 500 meters is basically all pure quartz sand. Beneath that 500 meters is a surface that we call an unconformity in geology. That's basically where we've had erosion, cut, and just remove material. So you have a gap in age between the sediments above and below, or in this case, above and the rocks below of the craton, the metamorphic rocks. In that metamorphic rocks, there's a series of faults, and those faults have carried hydrothermal fluids, which have deposited nice conductive minerals, which is what we're targeting here, right?
Exactly. It's these We're not targeting the uranium or the uraninite exactly, but it's the associated mineralization components, which is these big graphitic conductors.
Yeah, and graphitic just means, as it sounds, like it has graphite in it. It's got lots of carbon in it. And these, because they are bound by these faults, and the faults are roughly linear, they don't do any weird geometry. They provide good structural basis. They should be somewhat simple for the image segmentation. Is that correct?
Yeah, and again, maybe depending on the the survey type that you've used. So far, I've experimented with Magnetotellurics and DC resistivity. The DC resistivity, if you can't quite image all the way down to the our basement, it's going to be hard to get something that's going to segment out properly. However, in my case, it has been working out not too bad, and but that, since given that limitation, because with the sensitivity just decreases with depth for that kind of survey, the magnetotellurics though gives me that definition. I can get that resolution at depth. So that's so far for the basin kind of dipping conductors, it works really well. Unfortunately, that's not the most economical survey or easy survey to do in the basin.
All right, and you use two different surveys there: direct current, where you stick a bunch of electrodes and pump a bunch of current into the ground. You measure the voltage between points, and then magnetotellurics, which are
It's a passive method. So we're using sources that are, lightning storm down in the Amazon, or solar kind of solar influence. It's kind of the reverberation of the magnetosphere, and the signals kind of trapped from there. And
as the
then
trip.
those travel in plane waves, and those plane waves hit our ground, and we can measure the different frequencies. And each frequency corresponds to a different depth given a conductivity.
So I assume then, because of the differences in frequencies, you can look at really long wavelengths or to look deeper than what the direct current can, and that's why you can see these areas better.
Exactly. So if you record long enough for these MT and these low enough frequencies, you can see down to kilometers, even tens of kilometers. Not here, but yeah, the general surveys around here are low enough frequency that we get a good couple kilometers easily out of them.
Okay, so you were able to segment and get these structures, and how did it line up with what has been actually ground truth, which basically means drilled 500 meters down to intersect these things? How did it
Yeah,
compare?
I'm pretty fortunate. The place that the survey that I'm going over and using the data from has been extensively drilled. It's a mine already, so I had a lot of good ground truth, and lo and behold, it worked out very well. Compared to the standard L2, as we were talking about before, that smooth assumption, you really didn't like you couldn't really tell. You could see that there's a conductor, there's maybe a break in the unconformity, but you'd have no idea if it was dipping to the east, dipping to the west. Where do you plan your drill? Do you just drill straight down on top of what you have? You're not getting a lot of information. You're like, again, this is 500 meters here, so this is expensive drilling. It's not just cheap just to send a drill down. So we really need this information. And also, we've had seismic in this area, which lights up really well as kind of like another ground truth. And with the image segmentation, being able to just kind of it can see a lot of things. Like it looks at data, not just like a visual eye. So it can kind of find those boundaries a lot better, given maybe tweaking some parameters. But with that a little bit of influence, the regularization can be like, okay, I have something here, and it actually drives it home. It doesn't, it can kind of, for lack of a better term, latches on to the solution and keeps it pushing from there. And that was able to, yeah, recover. Maybe the dip was about pretty shallow, about 36 degrees. My estimation was about 40, 39. I'd say it was like 39.8. So, but I'll maybe have to call it 40. But yeah,
Significant
in
figures.
hindsight, yeah, significant figures exactly. But in hindsight, it worked really well in this application.
Yeah, I mean, to be fair, that's close enough for what they need it to do. They need to know rough direction and, plus or minus 15 degrees. If you get within that, to be honest, at 500 meters depth, you're doing amazing. It's a bit like
Exactly.
trying to throw a dart blindfolded, right? 500 meters away, and now you're giving them, you're taking off the blindfold. It's still 500 meters away. You still got to be able to hit the spot, but um,
Right.
you're increasing your chances for sure. That's pretty good. I mean, I think this is new, and in our opinions, we've opined over on this over beers. The industry work in is so slow in adopting new technologies and techniques. Will we see this any time soon?
Well, I'd like to say yes, but I have moved on and making I've kind of rounded out some of the edges that kind of came out of this study as it is. But yeah, it's kind of funny because the industry actually, I don't think, realizes how close they are to being able to do something like this. This code was back, the paper that I got the original idea from was from 99, and it's actually buried in some of the software that some of these industry leaders use. but nobody really understands or knows how to use them, or maybe it's like a lack of willingness to do it. Um, these tools are all here, but they're more, I guess, like Lego blocks. You got to put them together yourself and design it. But all these tools are available. But having someone push it and put it to a point where it's like, oh, I want to do image segmentation with structural information incorporated button. That takes a little bit more than just the science to make that stuff happen.
So, in other words, we have the tools, but we don't have a user interface to play.
That's essentially it. Unless you're willing to kind of dig into the blocks yourself and start building it. That's the unfortunate bridge where I guess there's the academia and then there's industry.
So you're going to build it for me?
Well, actually, I think
One
we
day?
do have it in our codes.
Well, at a level that I can use. I mean that's it's a pretty high bar, I know, but because around work for the listeners, I tend to break all the codes. It's a skill. I'm a bug tester by
Yeah,
accident.
it's a good thing. keeps our codes pretty top notch.
Um, okay, so what about AI and machine learning more broadly? I mean, we're talking about toys, we're talking about different how our industry is moving forward at a slow space, but it seems like AI, the possibilities are broad for use, and I just can't imagine somebody not using it. So is it going to be used more broadly, or is it already being used more broadly? Where's it going?
I think it is and it isn't. Like you said, the industry seems like it's slow to adopt, but there's also people within that industry that want this stuff. That they're paying money for the academia to research it and to make it happen. And yeah, I guess that's kind of where things, well, hopefully they're gonna go. Is that we're like, from my experience on being part of the SIMPEG group and being at the University of British Columbia, we're trying to take all that stuff and make it more simpler. So like even my next work after this paper is incorporating it more into being like more like a geophysical inversion, where you can be like, okay, here's my data, here's the regularizations I want to use here, or here's my assumptions, and then invert and then get our outputs. So I guess it's pushed academia enough that we're starting to like look at the problems that way, so that how do we transfer that knowledge a lot better. So I think from the academia side, we're definitely pushing that way, and industry, it's kind of up to them to hopefully keep up with what we're doing and pull it in. But yeah, the industry is so variable. Some people like what they have and just going to stick with it, or yeah, there's the people who are out there who want to adopt it and are kind of keeping up with what we're doing. A lot of, say, these newer companies that are coming out that are more like tech mining companies, they are full in, both dove in with both feet, and they're even on to the next level of doing things like prospectivity mapping, and that's incorporating more data than just geophysical data. So seeing the adoption of that, but until we start seeing, I think, a lot of like outcome from that, because I don't know, I can't really. Some people are saying they found deposits and they're finding things with AI, but I don't think that there has been a mine that's going to start anytime soon that was found by pure AI. But until I think on that step, until they can yeah, proving
Yeah, well, it's
results.
because they're also
Yeah.
looking for something, and they use a mine as a reason to, oh, I found the mine. Well, yeah, you found the mine. We knew it has existed 30 years ago. Like, it's already mined out. You're just finding a signature. It's like I've seen
Yeah.
geophysicists do the same thing. And they're like, oh, we need to invert and drill that. And you're like, no, that's the mine. There's already buildings there. It's this little spot over here that we're interested in. So, yeah, I wonder where that's going to go and whether or not our techniques are sophisticated for it. I also should really at one of the times go into like a historical look at my own industry and inversions, because what we used to do back in like the 60s is wild. All the inversions were done in people's heads, and it really came down to who you got for a particular area, because the inversion was all in their brain matter. It was not a repeatable solving of physics, unlike it is today. Today, it's a real science.
Exactly.
Back then, it was a dark art. Holy smokes. But before we move on and I get into the last couple of fun questions, is there anything you want to call out from anything from your project, your ongoing PhD work, or maybe the SimPeg group itself? I don't know. Anything you want to call out and bring up at this point?
Yeah, just I guess to promote a little bit of my future work. So the first kind of work here is building on, what is image segmentation and how can it be applicable to geophysics? And so I find a way to be able to apply that and, we can get some results. We can use that information. But it's kind of something that's abstract outside of the inversion. It's not really incorporated into it. Where my new work is now using actual this kind of the same equations that they do to do image segmentation problems, well, with images, say like deblurring. So if you take a picture of a fast moving car, you get a picture of the car, but everything behind it is a little bit blurred. So there's techniques that you can use that use image segmentation to correct that. And then you can actually kind of get your background resolved better. And upon reading those papers, they've been applying it to medical and all sorts of other applications. And now that I've now taken that and adopted that to the geophysical inversion, and then now it's kind of getting to that where you're saying like getting it into the hands of someone maybe in industry, they could use it a little bit easier. Maybe they don't need to understand all the crazy math behind it, but it still functions exactly like the tools that they're kind of used to. And and that's all done through the SimPeg framework. Where I'm actually part of the new initiative where we're kind of looking back at the optimization tools within there, and we're redesigning that so that we can plug in my ideas or even any others, like even using neural networks as regularizations themselves, being put into the SimPeg framework there.
Cool. Okay, so I want to ask one more joke I want to ask one more question before we get to the joke. You can see how excited I am for his science joke.
I am too.
Okay, so first things first. I know this is going to put you on the spot, and I know sometimes, because I've been in the field myself, you don't necessarily want to give out too much information to get somebody in trouble. But collecting this geophysical data is special in its own right. Like where you are, the people you're dealing with, the locations, the logistics, it can all be incredibly special. Sometimes it's not, but quite often it is. So perhaps a short story or an example from your own time in the field.
Oh boy. Well, let's do with a fun one, but also a devastating one.
Oh, it's both a tragedy and a comedy at the same time.
Yeah.
Shakespeare would be proud.
So I did actually a lot of work in China. We were one of the geophysical contractors that actually would do work, and we were able to get us in. We had an entity there as well. And it was in northern China. Kind of an old gold mine. So it's kind of more like maybe the foothills of Alberta. But again, everything has thorns on it. So everything wants to scrape you up and do all sorts of things. But it was really fun because it was a really large scale survey. We covered a lot of little small towns, and the helpers that came and helped us, they would invite us over to their house and have meals, and it'd be like they'd be giving us apples, all these fresh fruits in their fields that we were going through with our wires. And it was just generally a really good experience, except for when the mine site owner would come. And this guy, someone would hear his name and they're like, oh boy, we have to run. But it wasn't because he was a scary guy. It's because this guy really liked to party. And he didn't care if you had to work the next day. He didn't care if you had a deadline. He would take pretty much everybody from the mine out, and you'd go have hot pot, karaoke, and a lot of baijiu. So much baijiu. And I'm not going to name names because that's just to keep things a little general. But it was always scary because when you heard his name, you didn't want to go out that night because you're like, I have to go hike 30,000 steps minimum tomorrow, and
yes,
I don't want to. And when you're in different countries, you sometimes saying no is not culturally accepted. So you kind of have to say yes. So it was funny because people would run and hide and they would try to avoid these situations. It was like, oh, sounds fun. It does. But after, once every couple weeks, this guy comes around, you're just like, oh, I got to hide under my bed.
Yeah, for sure. Like it's no joke. It's you say, yeah, you're young, you're fit, you could do that one time. Yes, but you have to be doing that 30,000 steps, or depending on the terrain, it could be, 20 kilometers of walking, or it could be like 10 kilometers of walking, pulling wire, bushwhacking, whatever it is, but you're doing it day in, day out, day in, day out for weeks at a time. Sure, any one of those days, if you're relatively fit, not a big deal, but try doing that for 6 weeks straight. It's it's special.
Oh, yes.
So it sounds like that was an adventure, both fun and it wasn't very tragic. Slightly terrifying, unless you skipped over something tragic, in which case we'll leave it there and we'll go straight to the final question, because we're going to keep on the comedy instead of the tragedy. And your favorite science joke?
It might not be my favorite, but it's my favorite segmentation joke.
Oh, even better. The nerdier, the better. Come on, John, talk nerdy to me.
Okay. All right. So, why don't segmentation models ever fight?
I don't know.
They always find clear boundary first. I tried to make it as terrible as possible.
I don't know. I love it that it's thematic. That's even better. All right. Well, thanks so much for being on, John. It means the world to me. And for all those listening, he is one of the few people that have been listening to this podcast from the beginning. I'm so glad I finally got him on the podcast because he's awesome.
Thank you very much. Not too bad yourself.
Thanks so much for being here and enjoying Whimsical Wavelengths with me. Of course, this is the time of the show where I ask you to subscribe, tell a friend, reach out to me on social media. I actually had somebody suggest on Blue Sky that I should do a show all about why mammals wasn't able to take over the skies. We managed to take over and become apex predators in the marine sphere, as well as everywhere on land. Why not the skies? It's a pretty good, interesting idea, getting into the evolution of flight and just how evolutionary pressures really didn't favor mammals in that way. I don't know if I'll get around to doing that, but that's a really cool idea. I love it. Keep it coming. I'm serious. So yeah, subscribe, tell a friend, and I'll see you in 2 weeks.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's all waves. Colors weave stories painting the sky, swaying to rhythms as the galaxies fly by.